Hello everyone, this is Dr. Lennon, and we're going to be looking at functions for the next few lectures. So we're going to start with a basic introduction of functions, which is kind of a different way of thinking about formulas and ordered pairs and things like that ties them all together in a unified way. So let's jump right in and talk about what the definition is here. So a function, which I will often abbreviate by FCN period, is a rule which assigns each input to exactly one output. So it's a rule that maps things essentially. And we have some terminology there. So the domain is just a list or a set of all the inputs. Whereas the range is the set of all the outputs. So let's make a comment, so a remark. Functions are often thought of in four different ways. So you don't always encounter all of these for a particular problem, but just know that if you're looking at something, functions can often be represented in four different ways. So one, you can talk about a function in words. You can describe a formula by saying, okay, this function takes any input, multiplies it by 2, and then adds 7. That would be a way to describe a function in words. You could also talk about it by a formula. So we've seen lots of those with linear and quadratic formulas. Those are actually functions as well. So we'll have a special notation for functions, but really if you think about something like y equals 5x squared minus 3, that's a way to describe a function using a formula. And the last two are kind of linked. We can think of them as lists of ordered pairs. Describing a bunch of things that it represents, and then using those lists of ordered pairs, we can also talk about their graphs. So if you write down a bunch of ordered pairs, then you can determine the graph. Okay, so let's get back to that definition. So a function is a rule which assigns to each input exactly one output. So in this example, we just want to determine if a set of a bunch of lists of ordered pairs is a function. So determine if the relation represents a function. And a relation is just a fancy word for a set of ordered pairs. And we can ask what are the domain and range of each. So let's say we have a set with 1, 4, 2, 5, 3, 6, and 4, 7. So each input doesn't appear twice, and it has only one output. So yes, this represents a function. So the answer here is yes. So the domain, we would just list all the different x values. So the domain here, we have a 1, a 2, a 3, and a 4. And for the range, we're looking at the y values. So for the range, we have a 4, a 5, a 6, and a 7. So these are the answers to our questions. Part B, let's suppose our relation is 1, 4, 2, 4, 3, 5, and 6, 10. Again, we don't have any of our inputs appearing twice. We do have the same output 4 for both the inputs 1 and 2. But that is okay. We just need the input going to only one output. It doesn't matter if two inputs share the same output. So this one, a lot of times people will mistakenly say no here, but this is yes. It is okay for two different inputs to share the same output. So what is our domain here? Our domain has 4 values, again, 1, 2, 3, and 6. Our range only has three values this time because 4 is shared by both 1 and 2. And then we have 5 and 10. Again, when we're listing things with sets, we don't need to list duplicates multiple times. We just list them once. Okay, and for C, we have -3, 9, -2, 4, 0, 0, 1, 1, and let's say -3, 8. So we have 5 ordered pairs here. What's going on? Well, we see the -3 appearing twice as an input with 2 different outputs. So that's what's causing the problem here. So no, this is not a function. The input x equals -3 has 2 different outputs y equals 9 and y equals 8. So that's what causes the problem, and that's why this example does not represent a function. Okay, so probably you've had some exposure to functions like this before. A lot of times people aren't used to dealing with just the rule. We've already done some graphing before, so we're not going to do too much reviewing on graphing. But we will talk about a graphical test that determines whether or not something is a function. So so we were just using the definition here purely to determine if those lists were functions. But so a graphical tool to determine if something is a function is the vertical line test. So if any vertical line intersects a graph in 2 or more places, that graph is not the graph of a function. So that graph is not the graph of a function. So what this does is it doesn't necessarily tell you what a function is, it tells you what a function is not. So we can think about it. If we see a picture and vertical lines only hit the graph 0 or 1 times in any place, then that would be the graph of a function. So we can draw lots of pictures, lots of things that we look at and just use this to determine if it's a function. So example, does the graph represent a function? So let's just draw a bunch of pictures and see whether or not they represent functions or not. Okay, so we already looked at lines, a bunch of those. Yes, that is a function. No vertical line is hitting it anywhere in 2 places. We also have things like quadratics or parabolas. Parabolas, if they're opening upward or downward, yes, they are functions. But if you take that same shape and rotate it, say 90 degrees, you would end up with something that looks like this. And then you could have a vertical line that would hit 2 places. So that would instantly make this a no. And for similar reasons, other shapes that you would graph, say the graph of a circle, this would also fail. It would not be a function. You can have things that almost look like they're going to fail but don't. Let's say we had the graph of, let's say we were doing something like this, I don't know, and then the graph stops. We have what's known as a removable discontinuity and then continues onward. But then right at that moment we have a discontinuity. Let's say the graph jumps up for that 1 split second to that spot. Well, even if you draw the vertical line that goes through that shaded dot, it doesn't hit the picture at the bottom on the open dot. So any vertical line you draw still is only hitting 1 time. So this would in fact be a function as well. All right, what else could we do? Well, we can also do things that are a little bit exotic and maybe even boring. So I get a lot of students tripped up on this example. So what about if I just have one ordered pair and that's it? So think about that. Do you think that's a function? The answer here is in fact yes. It's not a very complicated function. The domain is just one x value and the range is just one y value. But it does in fact satisfy the vertical line test, right? You cannot draw a vertical line that hits that graph more than 1 time. By the same token, this is kind of a really weird one, but I'll show it to you anyway. So what if I don't draw anything? I just have an empty graph. Would you say that's a function or would you say that's not a function? So again, by the criteria of the vertical line test, yes, this is in fact a function. The domain is the empty set and the range is the empty set. This is known as the empty function. It's kind of a bizarre function. It just, according to the letter of law, fits the definition. It actually fits the definition vacuously. But if you think about it, you cannot draw a vertical line that hits it in 2 or more places. So for that reason, we say that that is a function as well. Maybe we'll do one more. Say we have something that, I don't know, zigzags back and forth like this. Again, this would be an easy no. We're hitting 3 times right here on this dotted line. So again, this would be a no. So that vertical line test is something that's a very quick way to determine if we have a function or not using graphs. Let's talk about function notation and plugging things in. So function notation. So function notation looks something like this. We have y is equal to f of x, and usually this is given by some formula in x. So this is known as the dependent variable. Or the so-called output. X represents the independent variable. Or the input. And then F is just the name of the function. So this is going to be useful if we're dealing with multiple functions that are kind of shorthand for these complicated formulas we want to work with simultaneously. So we see this notation a lot, and many times when we would write, say, something like y equals 2x plus 3, now we might write something like f of x equals 2x plus 3. So this is the nature of function notation, and the more you work with it, the more comfortable you will be. So let's just look at, say, plugging some things in. So in this example, let's say we have for the function f of x equals 2x squared minus 3x. Let's say we want to evaluate each of the following. So I'm going to give you something to plug into this function notation, and you're going to tell me what the output is. So f of 3 Okay, so what we do here is we just replace the x by a 3 wherever we see it. So we have 2, and then we replace x by 3. We still need to square it, and then we're subtracting 3 times 3. And then we just evaluate with order of operations. So we get 2 times 9 minus 9. So our answer here is 9. 18 minus 9. B, let's say we have, I don't know, maybe f of x plus f of 3. Well, we just found f of 3, so what we do is we have our 2x squared minus 3x, our f of x formula, and then we just add 9 to that. So that's all we would do there. What about if we start, say, doing function notation with other things, say f of negative x? Well, with this function notation, what you really want to do is you just want to replace whatever x is in the original formula by whatever is inside your whatever your input is in parentheses. So for instance, normally it looks like 2x squared minus 3x. Well, I'm going to take that x now and replace it with a minus x in parentheses. So I get 2 times minus x squared minus 3 times minus x. And so this becomes 2x squared plus 3x. The two negatives will cancel there and leave a positive. What about if I have something slightly more complicated? Well, I do the same thing. Let's say I want to do f of x plus 3. Well, now I'll do 2, and instead of x, I'll put x plus 3 in parentheses, and then square that, and then minus x plus 3. And that's how you use the function notation. You plug in whatever you see with whatever the original input is. It doesn't matter how complicated or simple it is. And then let's say we wanted to, continue, then we could, maybe FOIL this out. So we have x squared plus 6x plus 9 inside the first set of parentheses, minus x minus 3, and then we could simplify so that we get 2x squared plus 12x plus 18 minus x minus 3, and that will leave us with 2x squared plus 11x plus 15. And that would be the simplified expanded polynomial of what we have there. Okay. What about for evaluating domains and ranges? So primarily for us, finding domains. So let's just kind of two common things will cause an expression to be undefined. So one is division by 0. And another is, let's say, taking the even root, for example, a square root of a negative. I know technically I'm saying undefined here. Technically for number 2, an even root of a negative is just not a real number, but for the purposes of this class, we're just studying real values. So maybe I should say, to make that a little better, not undefined or not real. So when we see examples that ask us to find the domain, we're looking for those two things. So let's just do a few examples. We'll come back to these periodically as we encounter new functions. It's always interesting to ask what their domains are. But let's just do a few examples so you're kind of comfortable. So find the domain of each function. So let's say we have f of x equals x squared plus 5x. This is just a quadratic. There's no problems. We're not dividing by anything, not dividing by any variables, and we're not taking any roots. So the domain here is all real numbers. or an interval notation that would be negative infinity to infinity. So oftentimes in online homework, they're going to ask you for the interval notation to specify your answer. Okay, so let's look at a function g of x that has one of those features. Let's say 3x over x squared minus 4. So we can rewrite this by factoring the bottom, 3x over x plus 2 times x minus 2. So notice the domain is going to be all numbers except positive 2 and negative 2. Positive 2 and negative 2, so x equals plus or minus 2 causes division by 0. So we need to exclude those. So one way we can say the domain is x is not equal to plus or minus 2. In the interval notation, that's a little bit trickier. Basically, if you think about the graph, you have your negative 2 and your positive 2, and you essentially want to shade everywhere else. So because we have two open dots, we're going to have two union operators. So the interval notation would look like negative infinity up to negative 2, and then we'd union that with negative 2 to 2, and then we'd union that with 2 to infinity. So that is how you would write that in interval notation. Notice the two open dots kind of break it up into three separate shaded regions. So we have those three regions and then the two union operators that glue them together. Okay, let's look at C. Let's say we have h of x is the square root of 4 minus 3x. This amounts to just solving an inequality. So we require 4 minus 3x to be greater than or equal to 0 because we cannot allow a negative to be beneath the radical there. So this is the same as 4 greater than or equal to 3x. Divide by 3 on both sides and we get 4/3 is greater than or equal to x. So that's our domain here. And an interval notation that would correspond to, so x is all the numbers smaller than this, so we're going from negative infinity up to 4/3, and 4/3 itself is okay, so that gets a square bracket. Okay, now let's do one that combines both of those ideas. So let's say we have, let's go back to f of x. Let's say f of x is the square root of 3x plus 12 and divided by x minus 5. So we have two components here. So we require 3x plus 12 to be greater than or equal to 0. And we also need that x cannot equal 5 because that would cause division by 0 in the denominator. So let's go ahead and solve this inequality. So 3x is greater than or equal to negative 12. We divide by 3 on both sides and we get x is greater than or equal to negative 4. So if we think about the graph here, what's going on? The graph, we have the numbers bigger than negative 4, so we've got negative 4 here, so we shade it. We jump up to 5, but 5 is not allowed, so it gets an open dot, and then we continue shading to the right. So our domain here, if we write it in interval notation, we're going from negative 4 up to 5, and then we have to glue that together with the other region past the open dot. So that is going from 5 all the way up to infinity. And those are some examples of kind of typical domains that we'll encounter in this course. Okay, let's go ahead and look at those are some components of graphing functions, how we can tell if something is a function graphically or not, and talking about the domains and ranges. What about something where we don't know the graph of it? So graphing functions. Let's just do a couple examples here. So to graph a function, by hand. Typically, we make a table of values. Graph the ordered pairs. Until the shape is recognizable. A lot of times you don't see people doing it quite as much because we have programs and they graph so many points so fast. It's very easy to just type in the formula into a computer like Desmos.com and say, okay, there you go. But let's do a couple by hand just so we kind of remember how this goes in case we need to actually think about the construction of such a thing. So example, let's say make a table of values. And graph each function. So we'll just do maybe 2 examples and call it a day. Let's say we have f of x is, I don't know, let's say 4 minus x squared. Okay, so what we do is we have our x and our f of x that we plug it into, and f of x is really just giving us the y value on the graph. So let's say we do -3, -2, we'll plug in, say, 7 values. So here we would have 4 minus -3 squared, and that would give us 4 minus 9, which is -5. Here we would have 4 minus -2 squared, that would be 0. 4 minus -1 squared would be 3. 4 minus 0 squared would still be 4. And then we get some symmetry. 4 minus 1 squared is 3. 4 minus 2 squared is 0. And 4 minus 3 squared is -5. We could also extend our table if we want. We could make our x comma y pair. So our first pair is -3, -5, -2, 0, -1, 3, 0, 4, 1, 3, 2, 0, and 3, -5. So those are the ordered pairs. So we can use those to get our graph. Our smallest y value is -5, so I think I'm all right. And our biggest one is 4. So we have -3, -5. So we start off here. Then we have sorry, I did that at -4. I made too many marks. So we have -3, -5, -2, 0, -1, 3, 4, 0, 1, 3, 2, 0, and then 3, -5. So this is the general shape of our graph. We recognize the pattern is that downward opening parabola, and this is how we can get a quick sketch. So that's our graph of y equals f of x. So again, the procedure is a little lengthy, but we can go ahead and do that. Let's go ahead and check it with a program as well. Okay, so I'm at Desmos.com. I would recommend this program, especially if you don't have a graphing calculator. It's very nice and easy to use. We can just type in what we had there. F of x is equal to 4 minus x squared. And we'll get our graph. And you can notice that we're hitting all the points that we saw, down here at -3, -5, and so forth. And you can change the window using the wrench over here to make it bigger, or you can just click zoom in and out if you want to see it a little bit more clear. But a very fast way to graph something. Okay, let's go ahead and do one more graph. Let's say, let's try B. Let's say g of x is the square root of negative x. So notice the square root of x would only allow 0 and positive numbers. So if you have negative x, you can really only plug negative things into this. So notice the domain. So let's make that comment here. Note that the domain of g of x is negative infinity up to 0. So think about why that's true if you can't picture it right now, but let's go ahead and plug some of those values in. Again, since we're taking square roots, we want to be plugging in things that are perfect squares if we're trying to do it by hand. So again, we can do x, g of x, and then we'll write down our ordered pairs. So 0 we can plug in. We can plug in -1, -4, and maybe -9. So this would be the square root of 0, which is 0. This would be the square root of 1, which is 1. This would be the square root of 4, which is 2. And this would be the square root of 9, which is 3. So we can write down all our x, y ordered pairs if you want. We have 0, 0, -1, 1, -4, 2, and -9, 3. So graphing that, we can come over here and get, let's see. So we have 0, 0, -1, 1, -4, 2. I might run out of room here. 5, 6, 7, 8, 9, and -9, 3. So we get our picture. It's kind of this half a rotated parabola. And that's the graph of g of x. Okay, so we can go back to Desmos and check and see if that's really what it looks like, if we did everything okay. So this is the square root of negative x, and we get that picture going that way. So that's it for kind of connecting or writing down our formulas to creating the table, which gives us a list of ordered pairs, to graphing that on the plane. Okay, so that's it for functions, introducing them and also talking about the graphs. We'll continue in the future with looking at ways to create new functions for mold via arithmetic operations and composition and some other things. So this is Dr. Lennon signing off.